try that again. I didn't have the lapel mic on right, so you'll never see what this is the second time we're doing the video, and we had a bunch of technical errors. But here we go. So week 2.2 is going to be domains and graphs of functions. What we want to do is, the idea is we're going to look at starting, I'll intuitively show you how to find the domains of all your functions. And then once we have this, we're going to look at the graph of functions, and we'll look at a bunch of standard functions. And then in the next video, we'll start moving them around with transformations. That's the idea. All right, domains. The domain of a function f of x equals y. So if it's given as an algebraic expression, not the interval that you're going to give, the domain of definition, I guess, even, of a function which is given algebraically is all real numbers that make sense, making the expression true. Or valid. But that's not really how we find the domain. We find the domain by excluding the values which make sense. What are the two mantras for domains? Mantra 1 for domains is we can't have negatives under even nth roots. Even meaning n is 2k is divisible by 2. What does that mean algebraically? Algebraically, that means if you have an even nth root and anything underneath there, that immediately tells us that a of x has to be greater than or equal to 0. The second mantra, this will give us intervals for a temporary domain. And then all we have to do is make sure that we're not dividing by 0, and we have exactly what we want. So mantra 2 is don't divide by 0. What will that look like? If you have an expression b of x over c of x, this will immediately tell you that c of x, the denominator, can't equal 0. This is what we do. And then to find any domain, unless we have logarithms, which we're not going to really get into in this class, I might sneak in a little bit of them, exponential functions, but we're going to focus on trigonometric functions. With that scenario, these are the only two things you can have. You can have, first of all, you check mantra 1, and it'll give you intervals which make sense for algebraically for your function. And then you make sure you're not dividing by 0. This will be your domain. Eliminate the bad behaving points. The rest is your domain. That's the idea. Example. You don't get cute cats. They were in the first video, but now they won't show up, of course. Example. Find the domain of f of x, which is, say, x plus 1 over the square root of x cubed minus x. I'm running the mantras in my head. I immediately already see that I have both problems. I do have an even nth root, and I do have division. Let's do mantra 1. Mantra 1 says that because we have an even nth root, this immediately says x cubed minus x has to be greater than or equal to 0. A lot of people will try to start solving and moving this guy over, etc. What you want to do now is we want to use linear pieces of this nonlinear function to solve the nonlinear inequality. So we're going to factor x out of both terms. Then we're going to notice that that's a difference of squares. And we get this. Pictorially, if I'm already cheating because we haven't really done graphs, but if I already have used the curse of knowledge and pictorially cheat, what this is saying is this is exactly 0 at negative 1, 0, and 1. And then we're going to get this. Where is this function positive is what we want. It's positive here, and it's positive here. So between negative 1 and 0 and 1 to infinity. Those are the intervals that we should expect to get as our solution for this part of the problem. Then we make sure we're not dividing by 0 in there, and we're in business. Algebraically, how do we do that? You can also think of this on the real number line. We have negative 1, 0, 1. And then this is where it was equal to 0. So in each of these intervals, everybody is positive. Everybody's playing the same role. This is like it's your neurons, axon dendrites, if sodium is flooding or potassium is flooding. But the only place you can change is at the gates. So the only place you can change signs for your function is at -1, 0, and 1. Then in those intervals, everybody is negative or positive or negative or positive. So all I need is a representative in each of the intervals to find out what happens in the whole thing. That's the idea of this chart that I'm going to now do. The chart says that what I want to do is create each of these intervals, negative infinity to -1, -1 to 0, 0 to 1, 1 to infinity. Then what I look at is the roots of my functions. This will be x plus 1, x, x minus 1, and then our function, x cubed, the product of the three. So this is, remember, this is the root, -1, 0, 1 is the idea. Once I have that, and then what did I want? I wanted greater than or equal to 0. Now to fill in the chart, I just pick any representative in there. -2, I'll pick say -1/2 in here. I'll pick 1/2 in here, and I'll pick 2 in there. A nice number, the nicest numbers I can think of. All I need is 1 in there. Everybody behaves the same sign as that value. At -2, this will be negative, this will be negative, and this is negative. And then I multiply them together, and I get a negative. 2 negatives cancel, but I have a third, and that's not what I wanted. I wanted positive or not negative. In the next interval, -1/2, now this will become positive. The other two, -1/2 is still negative. -3/2 is still negative, but those two negatives multiply to give me my function is positive. This is where it's positive, in between -1 and 0. That's exactly matching. In the next interval, I pick 1/2. 1/2 is positive. 1/2 plus 1 is positive, but 1/2 minus 1 is negative, so I don't want that interval. At 2, now 2 plus 1 is positive. 2 itself is positive. 2 minus 1 is positive, so everybody's positive. And this was the interval that we picked, the idea of where this function was positive. So it gave us the temporary intervals, and I used the square bracket because it was greater than or equal to -1, 0, union, 1, infinity. This is my temporary domain or possible domain. The only thing now I have to do is run the mantra of don't divide by 0 in there, which we did have. This second part, which I'll squeeze in right here, this tells me the division now tells me that this x cubed minus x can't be 0. Square both sides. Tells me x cubed minus x can't equal 0 because 0 squared is still 0. This tells me that I factor it the same way I did for the other expression. That means those guys can't equal 0, so x can't equal -1, x can't equal 0, and x can't equal 1. What does that mean I have to do from this expression? I have to eliminate the values of -1, 1, and 0. So the square brackets where they were allowed to equal now become round brackets, and this is the domain of f. In this case, the denominator played no role here. Good. Now the idea is we're going to get the graph, which I'll define, and we want to look at the standard, a bunch of what we call standard functions and their graphs, and then we'll look at transforming them in the plane with these standard transformations in the next video. What's the definition of a graph? A graph is a subset. It's the collection of all the points in the domain and its image. So it's a collection of ordered pairs, which is a subset of R2. R2 definition. Let f from a to b be a function. The graph of f is all ordered pairs xy in the plane with specifically y equal f of x, i.e. we use the points x, f of x, which is in R2. The collection of all of these gives us the graph. So the graph of f, which we denote by GER, will be close enough, is actually a set. What is it? X, f of x, where we've checked that all of those values make sense, which we just did in the last example, showing you how to find that, where a is in the or x is in the domain A, which is a subset of R2. It's the curve that you trace out in the plane when you list all of these things. Let's do an example of a couple of them. So if you don't know what the graph looks like, you plot points like I'm going to quickly do. The idea is to use that idea and give you a bunch of standard functions so you know what their rough graph looks like, and then transform them around in the plane using the standard transformations. So example, sketch y1, which is x squared, and y2, which is sine x. If you don't remember what sine x is, I'm going to cheat a little bit and use some trigonometric values and the unit circle to compute these things, but I'm going to plot points. Solution. Here's what we're going to do. That wasn't very evenly spaced. It doesn't really matter. So what we're going to get is x squared, and then the point x squared. We're going to get x sine x, and then the point x sine x is the idea. So -2, -1, 0, 1, 2. I've cheated and done this, but you want to pick some points. I look at the domain. This is a polynomial. I run the mantra. Do I have any nth roots? No. Do I have any division by 0? No. The domain is R. Run the mantra. Do I have any even nth roots? Do I have any even nth roots here? No. So do I have any division by 0? No. So the domain is R. So the domain of these functions is both R. That's how I know I can pick any values for the domain. I don't know why those went here also. X is going to be -2, -1, 0, 1, 2. Here we're going to pick trigonometric values, so I'm going to start with the period of the function. Sine is periodic. It's 2 pi periodic. So I'm going to use 0 pi over 2 pi, 3 pi over 2, 2 pi. Slightly different values, but I can use any values in the plane and get nice values and see what the shape of it looks like. Here, what I'm going to get is 4. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1, 2 squared is 4. So I get the point -2, 4. -1, 1, 0, 0, 1, 1, 2, 4. What does that do for me? That plots the graph and it builds it at -2, I am 4. At -1, I am 1. At 1, I was 1. At 2, I was 4. If you build more and more of those up, you should see that it's a U, and we cheat and just say x squared, but that's the graph of x squared technically. In the next one, what we want is nice trig values. I'll use the unit circle values, and then the fact that the period is 2 pi, so this is pi over 2 pi, 3 pi over 2, 2 pi. And then I fill in the values. At sine of 0 is 0. Sine of pi over 2 is 1, 0, -1, 0. 0, 0. Pi over 2, 1. Pi, 0. 3 pi over 2, -1. 2 pi, 0 are the points we get. Here's 1. Here's -1. To sketch this now, I get 0, 1, 0, -1, 0. If you plot more and more of the unit circle values, you get that it's a wave. It continues in both directions. The moral of the story is, if you don't know what it looks like from its algebraic expression, you might have to use a unit circle with these weird transcendental functions or polynomials, plot some points, and then give yourself an idea of what the graph looks like. Then we can transform it in the plane. Let's list the first 5 standard functions that they call this and what you should recognize them as their graphs, and then we'll start moving around in the next video. Oh, I wrecked Fibonacci. Ooh, okay. Standard functions. And graphs. Categories, let's do category 1, I guess. Category 1 is going to be constants or scalars. What is that going to look like? F of x will just look like a constant b, where b is any real number. What is the graph going to look like? For any value of x, it's going to be the same. It's constant, and it should just look like if b was positive, this is what it'll look like. F of x equals b. What's the instantaneous rate of change of a function that doesn't change? 0. So the derivative of a constant will be 0 later on in the course. Category 2 is affine functions or straight lines. This will be y equals mx plus b. So m is not 0. If m was 0, it would be this case. There's going to be two cases, therefore. M can be positive or m can be negative. If m is positive, then you go from bottom left to top right. You're an increasing straight line. If your slope is negative, then you get decreasing. This is generally what the graph is going to look like. These are the first main categories. Next are all related to each other. The building blocks essentially of algebraic functions are polynomials, and the building blocks of polynomials are the power functions. All right, so category 3 is the main one. 1 and 2 are actually examples of power functions, but power. So let n be in z plus n greater than or equal to 2. Again, if n is 0, then we get x to the 0, which is a 1, which is a constant function. It would just be 1. If n is 1, then you get a straight line, or these affine functions. Or if n is larger than 2, we have two cases. F of x will equal x to the n, where n is odd or n is even. What will those look like? If n is even, it's going to look like the parabola like we just did. Ooh, squeak. It'll get more square as the powers get higher and higher. So x to the 10, say, and this one is x squared, like we just did. If it's an odd power, it will look like that, x cubed, and then the powers will grow faster. They'll intersect at 1 and minus 1, and they'll do that, say, x to the 9. You can only tell that if you draw them on the same graph. The next category is the inverse functions, which at MacEwan or the U of A, most of the time what they're going to do is they're going to leave inverse functions to the next class, 115, but I won't get into it. The next category is the inverses of these guys. In particular, this one fails the horizontal line test. This one doesn't, so we have to restrict to 0 infinity. Category 4 is the nth root functions. What do those look like? F of x is the nth root of x, or x to the 1 over n, where n again is greater than or equal to 2 is a positive integer. There are going to be two categories here, and that's why I wanted to draw them right below each other, because this one has an inverse, and an inverse is obtained by reflecting about the line y equals x. Long story short, we get there. Look at that one first. That's x squared. The inverse will be this guy, which we call root x. That's the moral. You need to know that it looks like that guy, and this is the first time we restricted a domain. Here, the inverse is reflection about that line y equals x again, but there's no restriction, so it's going to look like the s. This is the third root of x. If you compose these functions later, if you do this function following this one or vice versa, you'll be left alone. X will be left alone. We won't get into it, but they're related to each other. The next category is also related. It's 1 over, or reciprocals of the power functions, so they're going to call them reciprocal. All right, 5 is reciprocals of power. So this is f of x equals 1 over x to the n, or x to the negative n. There will be two categories again. If n is odd or n is even. If it's odd, it's going to be the hyperbola, 1 over x, like function. And you can't see it, but in here's the Atari function. And that will be 1 over x squared, is what I call it. That's roughly what they're going to look like, no matter if it's the even power, it'll look like this. Odd powers will look like this. I can give you one more, I guess, squeeze it in there. 6, the absolute value function. Y equals f of x equals absolute value of x, which is our first piecewise function, if x is less than 0. What does that look like? It's the two categories from case 2. What is it saying? It's saying if x is greater than or equal to 0, in here, you're just a straight line y equals x. That's a negative x if you're less than 0. So it's a v. This is y equals negative x. It's just two straight lines. This is absolute value. Next time we'll move them around with transformations.